So today we are going to be talking about something else new in our notes, combination circuits. And so we will have notes on that after the warm-up. And then you do have an assignment today, 1104.3 combo circuit problem set. But before we get to those things, we first need to go over this warm-up question. Like I said, the first part of it should be easy enough. You're just finding the equivalent resistance in this parallel circuit, which has 3 resistors. The second part of it, again, you know how to do it. We've looked at examples of it, and we've talked about how we would find this, but I wanted to see how you guys would do with it on your own. And I can't remember if it was in the homework yesterday, but it absolutely could be something you see on a test or something like that. So again, please make sure, if you weren't sure how to do it, copy it down. So we have a parallel circuit. It has an ammeter hooked up to it. You can see I've included what it might actually look like. We do have multimeters that look pretty much like this, and a multimeter is something that you can use as an ammeter or as a voltmeter or as an ohmmeter. It measures different things, and it just has a little dial, and you can turn it to whatever setting you need. And so you attach it like this if it's an ammeter. Okay, and so it's attached in a certain way. We're going to talk about how you connect an ammeter versus a voltmeter today in part of our notes as well, because it is something that you need to know. It was in the FET last Friday, but just to go over it again. So I included this, but when we actually look at the problems, you'll usually see it like this. So instead of the actual device, I just have an A in a circle. Okay, and so this is what my schematic would look like for the circuit in the warm-up. And so if I want to find equivalent resistance, this is a parallel circuit. It's not quite as simple as just adding 2 plus 4 plus 3, because again, as we add these resistors in parallel, we are also adding additional pathways. And so the equation reflects that. It actually shows that as we add more of them, we decrease our equivalent resistance. And this is the equation that we've been using. 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. In this case, we have 1 over 2 plus 1 over 4 plus 1 over 3, which you could add on a calculator, but if you want to do it by hand, you do need to get a common denominator, so I can't add them as is by hand. My common denominator for 2, 4, and 3, or at least the easiest one, the smallest one to use, would be 12. Okay, and so instead of 1 over 2, I'm going to have 6 over 12. Instead of 1 over 4, I'm going to have 3 over 12. And instead of 1 over 3, I have 4 over 12. And now I can add these together by hand. 6 plus 3 plus 4 gives me 13 over 12. Again, this is not your answer. This is 1 over your answer. You need to flip both of those fractions so that you have RT over 1 equals 12 over 13. 12 divided by 13 will give me 0.923 ohms, and that is my answer for this problem. Okay, so my equivalent resistance in this circuit is 0.923 ohms. Again, y'all should have been okay with the first one, hopefully. Okay, but the second question may have been a little bit trickier. It asked what the ammeter's reading would be at that position. Okay, and in order for you to answer this question, and I've mentioned this before, I'm going to very strongly encourage you to color code your loops. This particular circuit has 3 loops. One of them I've drawn red going through the 2 ohm resistor, one of them blue going through the 4 ohm resistor, and one of them green going through the 3 ohm resistor. And the reason I'm doing that is because of questions like this one. If I want to answer what the ammeter reading is, I need to know what portion of the current goes through that point on the circuit, because it's not all of the current. At that position, I don't want the total current. I only want the blue and the green. Okay, I zoomed in on it. Okay, and so if I wanted to solve for what my current would be at that point, which is what an ammeter reads, it reads current. If I wanted to solve for what my current is at that point, I need to figure out how much current goes through the 4 ohm resistor, that's my blue loop, how much goes through the 3 ohm resistor on my green loop, and I need to add them together. Or I could find the total current and subtract the red loop. That would also work. Okay, but I need to make sure I know which portions are going through there, and it's not the total. It's just those two. So if I want to find those currents, I know that I can use Ohm's law to find current because I know that voltage equals current times resistance. Obviously, my resistances are labeled. But in a parallel circuit, I also know what my voltages are. Because, again, any circuit, the voltage drops along a loop add up to the battery. Well, on the blue loop, there's only one voltage drop. There's nothing to add. It does have a voltage drop of 24 volts. This is a parallel circuit. And so I can say 24 equals I times 4, which means I equals 24 divided by 4, which is 6. I could do the same thing for my green loop. There's only one voltage drop. Therefore, the voltage drop is equal to 24 volts. That's going to be the case for every single parallel circuit. All of your voltage drops will be equal to each other. They will also all be equal to the battery. We've talked about that yesterday. Actually, we talked about it 2 days ago and again yesterday. But if I wanted to solve for it through this loop, through my green loop, again, I have a 3 ohm resistor, and I'm going to have a voltage drop here of 24 volts. I can plug those in. 24 equals I times 3, which means I is 24 divided by 3, which is 8. Okay, again, just as a quick little side note reminder, if this had been a series circuit, I could not do that whenever I was plugging in the voltage drops, because in a series circuit, they would be adding up because they're all in the same loop. They would add up to the battery. But because it's a parallel circuit, I know that I can use that 24 volts. Okay, so now I know what the voltage is through the 4 ohm resistor on my blue loop, and I know what it is through the 3 ohm resistor on my green loop. I just have to add them together. So I have 6, I have 8, so this is 6 plus 8, which of course is 14 amps. So the answer to the second question in the warm-up is 14 amps. Are there any questions about this problem? Okay, again, you may have to practice it some more, but it does help to color code the loops. So if you don't have different colored highlighters or different colored pens or pencils or markers or something, I would get that. I mean, you could use pencil and do like a dashed line and a solid line or whatever, but it's definitely easier to see if you have different colors. Okay, so this is what I was talking about at the beginning of the period. When we looked at the warm-up question, we saw this right here. This is how an ammeter is connected. And if you don't already have this in your notes, you should probably write it down. Okay, an ammeter will be connected in series. That means it's part of the circuit. The current has to flow through it. Okay, and so it's part of the loop. So if you look at the way that it's connected, you'll notice there's a gap in the wire on my circuit, forcing the charges that are flowing. If I'm looking at conventional current, they'll be flowing kind of in a clockwise direction, but forcing those charges to go in through this black lead into the device where it's actually measuring what the current is, and then back out through the red lead so that it can continue on its pathway. So it's actually part of my circuit. Okay, so if you connect an ammeter, it will be connected in series and it will measure current. A voltmeter, on the other hand, which you saw something that looked just like this in the FET. Okay, the FET also shows the voltmeter pretty similar to this, and you have to attach the leads to 2 different points on the wire. Now, a voltmeter is going to measure voltage or electric potential difference, which means you have to actually have a difference. You have to have a change in the electric potential energy being carried by the charges in order for the voltmeter to give you a reading, which is why we use voltmeters to measure across resistors. The charges have a certain energy going into the resistor and then a different amount of energy when they come out the other side, so we can measure the change. Okay, we can also measure the change across a battery, but a voltmeter is connected in parallel. It's not part of my circuit. The charges aren't actually flowing through it. It is simply measuring the energy at this point versus the energy at this point, and it's finding the difference. Okay, just as a little, again, side note, the energy change that it measures across the battery, because you could measure the change there, will be a positive change, and the energy change that it measures across each of those resistors would be negative, because it's, again, showing the gaining of energy in the battery and the losing or dissipation of energy at the resistors. Okay, so again, you do need to know how these are connected. Ammeters are in series, they measure current. Voltmeters are in parallel, they measure voltage or electric potential difference. Okay, when you see it represented in a schematic, obviously it's going to look like this instead. You won't see the actual device. So you're going to see the ammeter as part of the circuit. It's on the wire, it's in series. The voltmeter, on the other hand, is connected in parallel on its own little separate loop. Okay, and so it'll look something like that. As a side note, voltmeters, whenever you use a voltmeter, if you were to place it on a wire like this at the bottom of my circuit, this would give me a reading of 0. Because again, it's only measuring energy changes, and our assumption when we're dealing with these circuits is that there is no resistance in the wires, and therefore there should be no energy change in a wire. There should only be an energy change when we measure across a resistor or across a battery or a light bulb or some component where there is some change in energy, either positive like at the battery or negative like at those resistors or light bulbs or whatever other component you might have in there. Okay, so it does only measure change, which I already mentioned, but you can add that as well because I think there was a question like this yesterday that some of you may have gotten. They were randomized, but that would give you a reading of 0. That energy change I was just talking about, again, you've seen it before. We've looked at this animation, and you can see the energy of the charges represented here by their color. Maximum electric potential energy is red, minimum is blue. And so you can see there is a change in the battery. They go from minimum to maximum. There is a positive change in energy. Whereas if you look at what happens across R1, you start with this maximum energy. They start out red, and then when they go through, they dissipate, they lose that energy, and they end up blue at the end, and they have minimum. And the same thing happens through R2. And so that's the change that you would be measuring, is the change of the electric potential energy of those individual charges. That is your electric potential difference, or the voltage that you're going to get a reading of, which is why this one would give you a negative number and this one would give you a positive number. Okay, so that was just kind of recapping some of the stuff that we've already talked about, but now we're going to talk about something new. Combination circuits are the topic of our notes today. Yeah. Okay, the topic of our notes today, and so you're going to want to add this definition. A combination circuit is a third type of circuit that involves parallel connections placed in series. Alternatively, you could have series connections on one junction of a parallel circuit, although we don't typically do that in here. But the point is that this type of circuit is going to contain both series and parallel connections. And so if you look at the examples down here, you can see the one at the bottom left, if you were to trace the path of your charges flowing in your conventional current, you would have R1, everything has to go through there, but then you have a junction. And so you have a parallel section of the circuit where the charges either go through R2 or R3, and then they come back together, and that is in series with R4. And so we have these parallel connection that is in series with R1 and R4. This one, you have something similar. You have a resistor here, 4.5 ohms, in series with a parallel section. And so this would be another example of a combination circuit. So these circuits are going to be a little bit more complicated because you have more resistors. I've got 4 in each of these, although you could have one with only 3. And I also have some different types of connections, and that's going to complicate my math a little bit as well, because we had different sets of rules that we were using for series versus parallel. When we applied those that loop rule and that junction rule, it looked different in the series and parallel circuits. And so now we're going to have to take all those rules that we learned and combine them and apply them to situations like this. Okay, so before we get to the actual math and start looking at these new circuits, let's first start by going back over, and again, this might be a helpful thing to write down in your notes because this summarizes what we've done so far, but going back over what we talked about with our series circuits versus our parallel circuits, because if we're going to have to start combining the two, we need to make sure we understand how to apply the rules to each. So in the series circuit, we talked about how as we increase the number of resistors in the circuit, our total resistance increased. We had this equation that showed that. We also talked about how the current stays the same everywhere in a series circuit because there is only one loop. So the current going into a component on that loop equals the current coming back out, and then it goes into something else and it equals the current coming back out. And so pick any point, and the current will be the same at that point as any other point on that circuit. The voltage drops across each resistor or light bulb in a series circuit add up to the battery's voltage. Again, that was the loop rule that we talked about. The voltage drops along a loop add up to the battery's voltage. Well, guess what? There's only one loop. So now, again, we can find the sum of those voltage drops will equal the battery's voltage. We applied the same rules to parallel, but they looked different. Because when we added another resistor in parallel, we weren't just adding another light bulb, we were adding another pathway. And so our equation for equivalent resistance looked different. 1 over RT equals 1 over R1 plus 1 over R2 plus however many we had, 1 over Rn. Okay, and so that was our equation for our equivalent resistance. In a parallel circuit, we do have junctions where the current splits. And so we have branches of the circuit where you have maybe half the current goes one way and half goes the other. And so you can add together the currents along those loops. So maybe you have 3 loops, then you'd have I1 plus I2 plus I3, and that should give you your total current leaving the battery. We talked about conservation of charge and how you have the same number of charges going into a junction as coming back out, and therefore that means that you have the same number of charges leaving the battery as you have coming back to it. Okay, and so that's represented here. And then we also talked about, again, that loop rule. The sum of the voltage drops on a loop equals the battery, but in parallel there's only one voltage drop on each loop, so there is nothing to add. The voltage drops all equal each other, and they also all equal the battery. The voltage was the same everywhere. Okay, so those were the rules that we've talked about so far. When we applied Kirchhoff's laws to each of these different types of circuits, we came up with these relationships and these equations that we're able now to apply to series and parallel circuits. And you need to keep them straight because, well, one, you need to keep them straight anyway as you solve those individual problems, but now if we have a combination circuit, we're going to have to apply certain rules to certain parts of our circuit. And so that's going to obviously complicate things a little bit if you can't keep them straight. So again, you might want to have this copied down. I am going to move on. This is slide 69 if you need to come back and copy it down. All right, so let's look at this example. And again, you might want to copy it down in your notes. It says, calculate the equivalent resistance of the following combination circuits. And I'm going to take you through it step by step. It says we're going to do 3 steps. And so I didn't draw the whole circuit, I just drew the resistors. So you can imagine that these wires that are at each end are connected back to a battery. Okay, but just focusing on the resistors, if I want to solve for the equivalent resistance of that whole circuit, your first step is going to be to find the equivalent resistance for the parallel section first. So I'm going to focus just on this section right here. And we're going to solve for the equivalent resistance of that section using the rules for a parallel circuit. And so that's going to be 1 over 3 plus 1 over 2 plus 1 over 12 equals 1 over RT, exactly like it was in the warm-up and in the problems that we did yesterday. Again, if you're doing it by hand, you will want a common denominator, which is going to be 12. So this would be 4 over 12 plus 6 over 12 plus 1 over 12, which is 11 over 12. If I get the reciprocal or inverse, that's 12 over 11, which ends up being 1.091 ohms. Okay, so the total resistance of that parallel section, or the equivalent resistance, is 1.091 ohms. And there's a reason we've been calling it equivalent resistance instead of just total resistance, and that is because this is equivalent to, these 3 resistors in parallel are equivalent to a single 1.091 ohm resistor. Okay, and that's what step 2 is going to be. So step 1 is to find what that equivalent resistance is. Step 2 is to treat that entire section like a single resistor placed in series, because it is in series with the 1 ohm resistor. And so this whole parallel section has an equivalent resistance of 1.091 ohms. I can draw that and redraw my circuit with that in parallel with my 1 ohm resistor. And now I have 2 resistors in series. Okay, so this that's in green is equivalent to this. in green. Okay, that's why we calculated the equivalent resistance here. Okay, so now step 2, again, treat the equivalent resistance for the parallel circuit like a single resistor in series. Step 3, add them together like it's a series circuit. Okay, because they are in series with each other. So now we're going to add these two together in series like we would in any other series circuit. 1 plus 1.091 gives me an equivalent resistance of 2.091 ohms. And that is the equivalent resistance of this parallel circuit that you, or sorry, this combination circuit rather, that you see down here in the bottom left. Okay, so we're going to do another example as well, but it's the same process every time. Now, you could have one that looks a little different. If you had two resistors in series on one of these branches, you would add those together like they're in series first and then continue on like we did here. But I'm not going to give you one like that, other than I have a challenge one at the end. Okay, so let's try this one. Okay, it says calculate the total current and equivalent resistance for the following circuit. I'm just going to give you a heads up right now. You can't find the current in this circuit without first finding the equivalent resistance. Okay, we know that if we know the total resistance of the circuit and the total voltage, we can find current using Ohm's law, but we have to get the equivalent resistance first. So we're going to go through the same steps that we did just a second ago. I've highlighted the parallel section on this circuit because our first step is finding the equivalent resistance of that parallel section. Again, 1 over RT equals 1 over 3 plus 1 over 4 plus 1 over 12. Again, my common denominator here would be 12 if you were doing this by hand. This would be 4 over 12 plus 3 over 12 plus 1 over 12, which is 8 over 12, 2/3. Okay, so 0.667. Flip that fraction, 1.5 ohms. That is your equivalent resistance for that section. Okay, so again, step 1 was to find the equivalent resistance of the parallel section, and then we're going to treat it like a single resistor in series with my 4.5 ohm resistor. So now 4.5 ohms is in series with this whole section. This whole section has a resistance of 1.5 ohms. So we can go ahead and we can solve for that. Okay, if we add them together like they're in series, which they are, 4.5 plus 1.5 is 6 ohms. So that is the equivalent resistance for the circuit. So we found the first part. Now we can find the total current. Again, because I know my total resistance and my voltage is in the picture, I can just go to Ohm's law. V equals I times R, or you can write it like this, I equals V over R. My current equals my voltage divided by my resistance. My voltage is 6 volts, it's in the picture. My total resistance is 6 ohms, we just found that. 6 divided by 6 is 1. So the total current in this circuit is 1 amp. Okay, 1 amp is my total current. Are there questions about this example problem? No, not yet. Again, you are going to practice these today on your own, so if you do get stuck, then you can come back to these notes. You can also organize all of your data for this into a table like this. So if you want to copy it down, you can. Now, before, when we did tables like this, we had an entire column in our table for our series circuit where we had the same current everywhere. In our parallel circuits, we had an entire column where we had the same voltage drop everywhere. That's not going to be the case for a combination circuit. You're not going to have an entire column with the same number going down because now we're combining both sets of rules. Okay, so again, I would copy this down so that you have it to look at as an example, and we'll talk about how to fill in the rest of it. So I'll give you a second to do that. All right, so you'll notice that I have already filled in the resistances, 4.5, 3, 4, and 12, as well as the total that we found just a minute ago. You'll notice that I filled in the current that we found a minute ago, 1 amp, and that I labeled that as my current through the 4.5 ohm resistor because this will have the total current going through it. It has not split at that point. But I don't have the currents through the parallel sections, and I don't know what they are yet. What I do know is that they're going to add up to 1, because that's the total current coming into that junction. It has to be the total current leaving that junction. So it's going to split. If these were all equal resistors, I would expect to see 0.33, 0.33, 0.33. They're not equal, so I know it's not going to be the same number, but I do know they're going to add up to 1. I do also have my voltage drop as 6 volts, but you'll notice I did not fill that in for my parallel section. Yeah, so I did not fill that in for my parallel section because, again, it has to add with the 4.5 ohm resistor's voltage drop. Okay, and so that's what I have filled in here right now. Before we fill in the rest of the table, okay, I first want to answer a question like this. You will see this question again. Okay, this will be a question. One like this will be on the test.
Good morning, teachers. At this time, please allow.
So again, this is why it's so important to color code the circuit. Okay, I know it was important in the parallel circuit because we had all these loops. We have parallel sections here, but if you draw it here, you can really see where the current splits. You can see where you have the total current, and so I would recommend doing this, color coding those loops. So I've got a blue, a red, and a green showing the 3 different possible paths that those charges can take. Okay, but let's come back to the question. If each resistor is a bulb, which would be brightest? Again, this is a question that you're going to see on a test. You probably have it. I'm fairly certain it's in your assignment today. It might be in the one tomorrow. And it is definitely something that the district has put on the TEKS test in years past. Okay, so you'll see it again. And so let's talk about how we would answer this, because we talked yesterday about the fact that brightness determines power. And that's still the case. You could absolutely do all the calculations to fill in that table and get the brightnesses. However, you could also approach this conceptually. Because power is voltage times current, if we can determine which of these resistors has the greatest voltage drop and which resistor has the greatest current, and they happen to be the same one, well, guess what? That one's going to be the brightest. So let's go ahead and analyze it in terms of voltage and current and figure out if we can determine which one would have the most power without having to do any math at all. So talking about the currents, I have 4 resistors up here that we're going to say each represent a light bulb. Where do I have the most current? 4.5 ohms, 3 ohms, 4 ohms, or 12 ohms? Which one has the most? Do you have a guess? I'm asking, where's the most current though? Look at the diagram. Look at my color-coded loops. Which one has the most current going through it? 4.5. Okay, the 4.5 ohm resistor has all of the current going through it. Now, the other 3 in the parallel section don't have the same amount of current, and I think that's what you were referring to. I think you said path of least resistance. Okay, and yeah, so in the parallel section, I could also rank those. I'd have the most current through the path of least resistance, but it's still going to be less than the total because it's still just part of the total. So I have, if I ranked them, my current would be greatest in 4.5 ohms, and then 3, and then 4, and then 12. Okay, because you have the most in this series section here. So now we know where we have the most current. So now let's focus on looking at the voltage drops. Okay, so our voltage drops here, I know that in the parallel section, the voltage drops will all be the same as each other, but they're not going to be the same as the battery because I still have to add them to the series circuit. Okay, but all of those parallel voltage drops will be equal to each other, but they're going to depend on the total resistance for the parallel section. And we already found that a minute ago. A minute ago we did this math and we determined that the total resistance for the parallel section was 1.5 ohms. So this whole thing is 1.5 ohms. And so if I'm trying to figure out where I'm going to have a larger voltage drop, okay, it's going to be where I have more resistance. Okay, and so I have more resistance here. 4.5 is bigger than 1.5, and so I will have a larger voltage drop at the 4.5 ohm resistor than I will at all the other ones. The other ones are all equal to each other, okay, but they're going to be less than the 4.5 ohm resistor. And this is why I said that it would be helpful to analyze this in terms of just the conceptual stuff. We don't have to do any math because guess what? We have the most current through the 4.5 ohm resistor, and we have the most voltage through the 4.5 ohm resistor. And because those are both the greatest values, they're going to give us the greatest power. So without doing any math, I already know that the 4.5 ohm resistor will be brightest because it has both the largest current going through it and it has the largest voltage drop. It's going to give me the largest power. Now, could I solve it mathematically? Absolutely. Okay, and I would recommend that you do that, you know, if we were trying to solve for that number. But if you can answer a question without having to do the math, do it. Okay, because it is obviously faster than having to go through all the math. By the way, if you do have a combination circuit and you have a bulb that is in series with a parallel section, that one is usually the brightest. If they all have the same resistance, it would be the brightest. Because these were different resistances, we did need to check. Okay, but it's usually the one that's in series that ends up being the brightest because it has, like we just said, the most current and the largest voltage drop. All right, back to our table. Okay, so back to our table, I have down here the steps that I would recommend that you use anytime you're solving a combination circuit. And they're kind of small, so I'll read them out loud. If you want to jot them down, you can. But I would recommend that you start by solving for the parallel resistance and then the total resistance. We already did that. We found the parallel resistance to be 1.5. We got the total to be 6. Step 2, solve for the total current. And we used the total resistance and the battery to get that. That was 1 amp. And we were able to set that equal up here, 1 amp, because all the current flows through that resistor. That was step 2. Step 3 is to solve for the voltage drop in series and subtract it from the battery to get the parallel section. The reason I say to do that, it's faster. If I look here at my numbers, I know the resistance and the current through this 4.5 ohm resistor. I can absolutely find the voltage. V equals I times R. 4.5 times 1 is 4.5. Okay, that voltage drop has to add up with the voltage drop in the parallel section to be 6. Because again, the voltage drops along a loop add up to the voltage of the battery. And there's 3 loops here. Okay, these are all the same as each other, but they're all also going to be the difference of 6 and 4.5. 6 minus 4.5 is 1.5. Okay, and so the voltage drops at each of those parallel sections, they're all 1.5 volts. Okay, so that the total on each loop is 6. 4.5 plus 1.5, 6. The next loop, 4.5 plus 1.5, 6. Okay, your parallel section will have the same voltage drop within that section. So they're all going to be the same number. From here, hopefully you can see what you would do next. I can now find all of these currents because I know the resistances and the voltages for each. I can figure out how much current goes through each branch. And then, of course, I could solve for my powers after that because once I have current and voltage, I can find power. And you could figure out the brightest bulb that way, but it is more work because you have to do the math. Okay, but those are the steps that I would follow. I did not go through and solve all of these, but you're welcome to if you want to open up this particular slide and finish filling this out. I'm on slide 79. Okay, here's another example if you want to try one more practice problem. And in this one, again, same steps that we just talked about. So we could start by solving for the parallel resistance. Using these values. In this case, I would not try to find a common denominator and solve this by hand because that's 8.7. Okay, so that would be kind of tricky. So I might just go straight to the calculator for that one, but it's kind of up to you how you want to approach this one. But you're going to want to solve for the parallel resistance and then add it to 5 to get your total. You know the total voltage is 9, and so once you get this total and this, you can solve for this and then follow the steps that we just talked about. So again, if you want to look at this one as another practice problem, it is on slide 80. However, for the rest of the class period today, I'd like to give you some time to work on your assignment 1104.3. Combination circuit problem set. It is due by 11:59 p.m. tonight. However, I'm going to encourage you to get as much of it done as you can in class today. That way you can help each other if you get stuck, or you can ask questions of me if you need any help. If you do finish early, I'm going to encourage you to work on the unit summary, and you can use that for additional practice because, guys, if you're not paying attention, your test is next Wednesday. Your quiz over this unit is on Monday. We have actually finished all of the topics today that we're going to be covering. That was it. Combination circuits was the last thing. Tomorrow we'll have more time to practice. We'll do a couple more examples, but we've covered everything. So you need to start getting ready for the test, and the unit summary is always a helpful review. All right, guys, if you have questions, let me know. Otherwise, I'm going to let you get to work.